If you've looked at query execution plans back in SQL 2000, you might be wondering at this point, why isn't SQL Server showing me the bookmark lookup? And the bookmark lookup was actually displayed in SQL Server 2000 as an operator right there by itself. But it was only a logical operator, and what that operator was doing was hiding the clustered index seek, or a RID lookup, or a key lookup, or some method of finding the data in the clustered index. And then it was hiding the join loop where it put that data all together. So, although we don't see these as bookmark lookups and we have to be able to interpret them, at least it's not hiding the fact that it's doing another search and a join to get the information together. So it's exposing all the physical work it has to do for a bookmark lookup. But I'm still going to call them bookmark lookups. Another thing to point out here is that as you look at multiple different query execution plans, you'll see different ways of doing these joins, whether it's a nested loop or a merge join or a hash match. And generally, SQL Server is going to be choosing the best one depending upon a couple of factors. First is the size of the data involved, whether it's merging 1,000,000 rows with 10, and whether or not the data is coming to it already pre-ordered, so it can just quickly fly through that information. Let's look at another query. So, query 3. Here we're going to select from our table columns 1, 2, and 3, and our search argument is where column 4 is equal to 319. Now, the non-clustered index here has column 4 in it, so that's a perfect index for finding the right rows. But if that's all we had in the non-clustered index, it could find column 4 and find column 1, but it would still have to do a bookmark lookup to go find column 2 and 3. What we're going to do is include column 2 and 3 at the leaf level of the non-clustered index so we can build a covering index. So that's what we're going to do. So product 4 is part of an index, a non-clustered index. If we jump back over to here, we can see there it is. This would be column 1. Well, here's column 4, but then here's a column not included, the transaction date. And if we run this, we'll see it had to do that bookmark lookup. This is what we want to avoid. And this time it ran very fast because we're just finding one row. But if this was a very common query, I'd still want to remove that bookmark lookup. So what we'll do is we will find here this index seek, and the index seek was on in the object there. You can see IX transaction history, product ID. That's the index it hit. So we'll jump over here and open up these properties into included columns, and we want to include transaction date. So add transaction date. OK. And click OK to rebuild the index with the new include column. There it is. So let's re-execute the query. Bingo! This time we see just an index seek, a perfect covering index. Just for fun, let's see what SQL Server does when we throw one more search argument at it. And execute. And let me explain what this is doing. Here's the index seek, just like it was before, but then it has to also filter by quantity greater than 10. So SQL Server figures the fastest way to find where both product ID equals 319 and quantity is greater than 10 is to first limit the rows down to only those where product ID equals 319. And it does that using the index seek just like before, hitting that transaction ID. You notice that the output list includes the transaction ID and the transaction date, so it already gets that data there. It returns 118 rows, which is a very small, tiny subset from 113,000 rows. Then it has to go do a bookmark lookup to go get the rest of the data. And it needs this so it can find the quantity column, joins that together in nested loop, and then here's a filter where it goes and filters that down to those greater than 10. So to wrap this up, talking about indexes, the whole idea of indexes is to somehow build a bridge or a shortcut between the queries or the questions and the answers or the data inside the table. And you're only going to be able to identify and build good indexes when you know what the query is going to be and how the data is organized inside the table. And to build those shortcuts, you want to build clustering indexes or covering indexes to try to avoid bookmark lookups for those common queries. We could talk for hours on strategies on how to build indexes, but most of this you'll be able to figure out yourself if you understand how they work inside. And that's what we've been talking about. The meat of what a clustered index is, a non-clustered index, the include columns, and those covering indexes. One last thing I want to say about indexes is there's a common myth out there that the competition between an OLTP and an OLAP database, meaning an online transaction processing database and a database that's used for online analytics, or BI or data warehouse, is the number of indexes, where they say in this myth that if you add lots and lots of indexes for a database designed for reporting or analysis, that's going to be a bad thing for online transaction. And it's true, there is a cost to updating an index. However, that cost is not as great as this myth might promote. I believe the real conflict between a reporting database and an online transaction database, or a database being used for those two purposes in competition, has to do with the locks and the contention between users who are trying to lock data for reads versus people trying to write to the database. And we'll get into that in the next lesson. Even an online transaction database needs to have good indexes so it can find the row quickly to update or to find the row quickly to select. So there you have it, indexes. As long as the schema is good, meaning the text of the book, and the queries are good, meaning the questions you want to answer, an index provides a good fast shortcut which gives you good performance.